Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Ruming Peng, who will be talking about internet background radiation.
Thank you. Thanks for coming to this talk. In this talk, we are going to look at a very special type of internet traffic, which we call internet background radiation. And the name background radiation comes from the cosmic background radiation in the physical world, which is very low energy and very uniform microwave radiation that can be observed everywhere in the universe. And many believe that this is the afterglow of the Big Bang. And for this reason, by studying the pattern of our cosmic background radiation, as shown on the left picture, we get better understanding about the formation and structure of the universe as plotted on the right picture. And let's see how much this analogy holds when we look at internet background radiation. I should also add that please feel free to interrupt me with questions anytime. I like questions. The internet background radiation is a baseline noise of internet traffic. And like cosmic background radiation, can be observed everywhere. And here it means at any IP address, even an IP address where there's no computer attached to it. We can continue to see packets constantly coming in, hitting the IP address. And in this talk, we'll look at what it looks like and why it exists in the first place and what it can tell us about the internet. And as I mentioned, we can observe background radiation on unused IP addresses. And this is exactly how we are going to measure it. We monitor an array of unused but globally reachable IP addresses, which we call our network telescopes, and to observe the internet background radiation. And the natural advantage of watching an unused address is that we do not have to separate normal traffic from internet background radiation. It can be either case, but in our case, the addresses have never been used. And our main telescopes are located at LBL. There are two of them. Each have 5 Class C networks that translates to about 1,300 addresses each. And we also have telescopes at University of Wisconsin, which are much bigger, but we have it for a shorter period. And we also have much smaller telescopes located across Planck Lab. So before we go on, let's look at a bit of background. Why do we study it in the first place? Why does it matter? It turns out that by observing internet background radiation, we get to study the malicious programs on the internet, which we call internet malware, in action. And if we do not only passively monitor traffic, but instead try to talk to them, we get the chance to talk to those malicious programs face to face, and we can figure out what they are up to. And that's why it matters. And for this reason, there has been quite some work in this area. It has been quite active in the past 2 years. First, there were studies of denial of service attacks by looking at the backscatters observed on very large telescopes. This is mostly done by Moore at CAIDA, UCSD. And there are also studies of specific worms. And for example, for this witty worm, they were able to identify the patient 0 at a particular military base. And with that information, they were able to track down the original worm author, which is very cool. There are also efforts in building good honeypots that emulate computers. There are low interaction but scalable honeypots, such as HoneyD and iSync. And there are also VM-based honeypots by the UCSD team recently. And also, there are interesting work from Internet motion sensors. Their work has been focusing on the distributedness of our telescopes that they have. And in this context, our study is the first broad characterization of Internet background radiation, in the sense that we are not looking at any specific aspects of our Internet background radiation. Rather, we are looking at the broad picture, the global landscape of the background radiation. And our focus is traffic semantics, that we decide the big picture should be about what the traffic is trying to do, rather than, for example, TCP IP level characteristics of the traffic. Yes?
So why do you need to look at traffic as a instead of
We'll see in a bit, but the quick answer is that the TCP IP level does not tell you information detailed enough about what the traffic is really trying to do. For example, there are a lot of things going on in Windows RPC protocol, and various sources are trying to do different things at Windows RPC, but they all appear at the same port. So by looking at the port number, we cannot really tell much about it. Yes?
I want to go back to the question that Bill asked. So you said that you use addresses that were never allocated or never not used. So I mean, the adversary can also know that information and avoid maybe back into that space. So wouldn't it be better to actually take the allocated space and take a chunk of that and basically never initiate any communication from that chunk? See what comes back to that. So then you have a better.
Yeah, I think that's a good point. So in reality, the address we used is a subnet of our LBL's address space. Ordinary people do not know which subnet is used and which is not. However, there are additional considerations. For example, they can try to do a reverse DNS lookup and see whether that has a DNS name associated to an address. Usually, the sources do not go such lengths to determine whether a host is live or not. But we do have telescopes that have our DNS name associated with each address. So even that can be observed. But for example, on a larger scale, as we publish this work saying that we have telescopes at LBL, then they can encode that information in their code, saying that we want to avoid LBL altogether. And currently, I do not see any reason that they want to do that. They simply have no incentive to avoid them. But in future, this will be a problem. So if we really want to put it into use, for example, for malware defense, then we probably need to have a distributed set of telescopes that we hide their identity from the attackers.
You basically want to look as similar to normal hosts as possible, except that we don't initiate communication.
Yeah, this is a very much open question, whether the attacker can distinguish a honeypot from a real computer. And so as I mentioned, our focus is trying to understand what the traffic is trying to do. And since this is the first work in this regard, an important part of the contribution really lies in developing the measurement methodology. That is, how do we keep a lot of conversations going on and also analyze these conversations to extract the meaning of the traffic on a large scale. And this is what distinguishes this study from other works in this area. So, however, before we delve into the meaning of the traffic, let's look at the appearance first. And what I'm going to show you is a live replay of our background radiation, which is collected April the 1st. I hope the date does not bear any influence on the traffic we see here. And at any given moment, you can see that there are usually a couple of hosts that are doing sweeping scans through our telescope addresses with ICMP packets, very short ones. However, if we occasionally, there are also TCP SYN requests that are connection requests from other hosts. And what we find is that usually these TCP SYN requests are from different hosts every time. So we can see that there are random probings appears, and there are also sweeping scans. Another thing to notice is that the source addresses are not very adjacent to the destination address in the address space, suggesting that the traffic might be coming from remote corners of the internet. And indeed, if we plot the hit pattern with x time on the x-axis and the destination IPs in our telescope on the y-axis, we can clearly see two kinds of patterns. There are lines representing those sweeping scans, and there are seemingly random dots that represent those probings. So this is the first sense of what it might look like. And let's look at the numbers. So the very first question we might ask is, how often do we see a packet if we just look at one IP address? So based on our data over a week in February, average on one telescopes, the number is about 342 packets per day per destination IP, which translates to about one packet every 4 minutes on any IP. However, there are two caveats here that we haven't claimed that the radiation packets are evenly distributed among destination addresses and also are evenly paced over time. Let's look at whether there are any hotspots or bursts here. This plot shows the distribution of packets over destination IPs, which is on the x-axis. And the y-axis is the number of packets received over 1 week period over these IPs. And we can see that there are a few hotspots here, yet the hotspots are in fact not so hot because each of them represents less than 1% of the total number of packets. There are also interesting several low points which correspond to addresses ending with 255. And those are usually broadcast addresses of subnets. And it seems that the radiation have some intelligence in avoiding those addresses. But overall, we can say, yes?
Could it be that the sender just sent to that address and it doesn't translate into going to your... Are you saying that what are you saying that there's intelligence in avoiding? Are you saying that that's a function of the network or of the malware that you're monitoring?
I think that's the characteristics of the malware. They just avoid sending them, because the traffic is captured at the internet gateway, so those packets are not dropped when they hit there, I believe. Yeah.
Okay.
Well, so the router usually be throwing away all the ICPs to that address?
Yeah, that's also a possibility. Yeah, that's a good point. I haven't thought about that before. So it might be possible certain routers drop those packets. Yeah. On the other hand, not necessarily all addresses ending with 255 are broadcast addresses. But although rarely are they really used as normal addresses, but usually, for example, the subnet is larger than a class C, then only one address is broadcast. Yeah, that's certainly possible.
So have you looked into the hotspots?
I looked into them, but I cannot find anything unique about them.
Yeah, I was going to ask you, so are they like the .1s or the .254s, or are they more concentrated on the lower half of a, slash 29 or 30?
This one is .8, and I believe that one is .9 or something like that. But
there's no pattern your source has where there was one where you could source or something.
yeah, so my take on this is, in general, if we look at packet volume, as we will see in a moment, they are usually generated by a small population of our sources. So in that sense, it might be hard to reason why they are like this, because it can be just due to the peculiarity of those source hosts. Perhaps another way to look at that is actually to see what kind of what fraction of source population is doing, so that we are looking at a large number of sources, and so whose behavior are usually easier to reason why they act like this. And therefore, we look at the volume from another dimension by looking at the number of distinct source IPs we find per destination. And we find that the number of source IPs are also quite evenly distributed. There are likewise low points here, and there are also hotspots, which, however, do not correspond to those hotspots in packet volume. Yes.
So it looks like some of the scanners don't look
Yeah, or maybe they are dropped, which is also possible.
Is it the same hotspots every day?
That's a good question. I believe they are not stable. My recollections. Let me see if I have a slide on that.
So if they are not stable, if you look at the distribution over a longer period, they might be more evenly distributed.
Yeah. Certainly, we can, for example, compare 2 weeks and see whether they're stable or not. But the fact that they are actually not so hot does not bear any significance of why they appear. Yeah.
So my experience looking at stochastic processes is that it really helps to actually be able to say, to like run some statistical test and say, with 95% confidence, these are hotspots. This is not just, oh, well, it's a Gaussian process, and sometimes there are hots.
Yeah, that's a good thing to look into, yeah.
Okay. So you haven't done that?
No, I haven't done that. Yeah, as you will see, our look at the appearance is really shallow in the sense that we are just trying to get a first sense of the traffic, what the traffic might do, and our sense is that the traffic is automated, and what we are really interested in is to get to the meaning of the traffic, what they are up to, what's the intent. So this is the distribution of sources, and we can claim that the destinations addresses in our telescope are treated almost the same in terms of source IPs and packet volume. And we can later we can see what this observation bears in how that affects our design of our honeypot system. And now let's look at the variation over time. This time we see clearly there are variations. There are diurnal patterns, and in particular there are lunchtime spikes. And if we look closer at the lunchtime spikes by breaking down at transport layer, we find that those lunchtime spikes are largely ICMP pings. And not shown in this plot is that they are coming from a small fraction of population. So again, we might want to look at from another angle by looking at what the larger population, fraction of population is trying to do. Yeah, this is West Coast lunchtime. However, it doesn't necessarily mean it's a lunchtime at the sources. So.
Well, I was mentally trying to push this.
Yeah.
So why do you think it's a long time as a peak? I mean, if the radiation comes from different sources, for example, there are models on East Coast, my sense is it's long time peak at East Coast.
Yeah, my sense is that those small fraction of sources that create these spikes are coordinated. And there are other evidence suggests that some groups of sources are actually coordinated.
But when you just look at your previous slide, look at the distribution of the sources, it seems to be evenly distributed. And you also said they are not stable. If they are not stable, why the larger
Can you elaborate more on the stableness of what?
in the previous slide,
Yeah.
the graph showing that the distribution of the packets comes from different sources.
Yeah.
You said the distribution is quite even.
Right. Well, the even distribution can due to two effects. One is that one fraction of the sources are doing sweeping scans. So every destination address will be hit by the source address. And another fraction of the source addresses are randomly probing. So in aggregation, we get almost about the same amount of source address for each destination. So I believe that does not conflict with this. And yeah.
What I mean is if there's, as you explained, if there is a small number of source IP that collaborators try to do such scanning,
Yeah. Yeah.
and show up to this pattern.
Yeah.
And simply the full expression also shows certain source IP addresses with higher
Yeah, but those IP addresses are really hitting the whole address space. That's why in the previous plot we did not see the effect.
Do you know how many, sort of trying to visually do the integration work, how many packets are represented in this graph and how many packets are represented in the graph? Volume-wise?
I'm sorry,
So if I integrated across time the number of packets here,
yeah.
just any sense how many packets that is, and then just comparing that to other, because it may be that this is a very small fraction.
So, yeah, are they plotted in the same period?
Yeah, they're plotted in the same period. So the aggregation will be the same. The same as, oops, yeah.
Did you look at, this is from one telescope in one
Yeah,
space.
yeah.
That seems interesting.
Yeah, yeah.
Did you compare this to one of the, said you had lots of telescopes, did you look it up in space?
Yeah, that's a good point. We looked at, for example, our University of Wisconsin telescope. And what we found is that the sweeping scanners tend to be local, that they tend to scan a particular portion of the internet. And therefore, we do not see those clear lunchtime spikes at the other telescope that we looked at. However, the diurnal pattern still is there, that we do see more packets during the day and less at night. Right.
So, because I was thinking maybe what's happening is you're getting sweepers that scan the entire internet one day, and when this happens, it just depends on where you are in the address space.
Yeah, that's certainly possible.
But it sounds like that's not what's happening.
It does not. It might be the case that the scanners are skipping certain portions of the internet space and does not hit the Wisconsin.
Does the Wisconsin graph look like this except that it's at a different hour today?
No, it does not look like this. It does not have these high spikes. It might be due to the reason that the Wisconsin telescopes are larger, therefore the sweeping scans are aggregated together so that the spikes are not that high. But we do see diurnal patterns at the Wisconsin telescope. I wish I can have a plot of that.
What time of year was this collected? Particularly was school in session or not?
That's a good question. It's February 20th this year, February. So it's hard to say whether it's school year or not. However, this kind of pattern persists over the past 2 years. So it's the same in April 2004. But the volume is different. It was higher 2 years ago. But we still see spikes like that. And as I said, since the packet volume can be affected by a small number of sources, maybe we should rather concentrate on the larger population of the sources. And so we can look at the variation over time by looking at the number of distinct IPs we see per hour. And we find that there are also variations over time. And there might be certain daily patterns, but it's not clear. And again, maybe some stochastic process may help us determine whether the pattern is daily or not. But one thing we noted is that those variations are not correlated to the spikes in packet volume, suggesting that they're independent of each other.
So
And again, breaking down by transport layer, we see that most sources are sending TCP connection requests rather than ICMP ping packets.
So, because in the last graph that you had, like this, the red lines were the ICMP ones.
Yeah, yeah.
So what's going on is the ICMP traffic is high volume and TCP traffic is high number of sources.
Yeah. So a brief summary of what we can see by just passively watching those destination IP addresses. There's a near uniformity among destinations. However, the caveat here is that that's for nearby addresses in a telescope. If we look at telescopes at different places, then they will be different. There are generally two kinds of hit patterns, sweeping or random. And we also see variation over time in both in terms of packet volume and number of sources. And also, what's interesting is the traffic is dominated by ICMP pings and TCP connection requests, which suggests that the sources are expecting replies. And we can, yes?
What do you mean by nearby addresses? I missed that.
What I mean is that the addresses are close to each other. And what happens is that the sweeping scanners usually operate locally, so that if we look at an address place that's far away, then we may not see the same kind of pattern.
So all the things you saw were mostly from nearby addresses? The sweeping address?
Yeah, yeah.
Okay.
Yeah.
I guess if you want to confirm this, you can look at the IP address and try to encode the rest of the see if they are in the same time.
Yeah, I can certainly do that. Yeah, yes.
Why do these scanners speak linearly? If I were using a scanner, it might be better to use like a serial membership layer to kind of hop around. Every address wants to hop around, so it appears to be more linear.
I guess the answer is there might not be enough incentive for them to be clever. They can just be dumb and get almost the same kind of return they get by scanning linear. Yeah, certainly in future they might evolve to the pseudo-random scanning. And what we can say is that the traffic appears to be highly automated and very intentional. So the natural question is, what do they want? And let's see. And in order to see what the traffic is up to, we replace the passive observer with a honeypot. And we use the honeypot to create conversations with the sources. That entails answer ICMP pings, establish TCP connections, and reply to application level requests, for example, web requests or whatever protocol we see. And until we find out what the intention is. And there are three key elements in building such a honeyfarm. First, we need to build a honeypot. And the key challenge here is how to build those application level responders that can carry on the conversation. Also, since we are responding on thousands of addresses at the same time with limited resource, we need to create filters to reduce the traffic volume, yet get the same kind of visibility we get by responding on those addresses. And finally, we need to have an automated way to understand the meaning of the traffic from a large number of connections every day. And let's look at them one by one. In building the honeypot, our principle is to be as sweet as we can. That means to say whatever the sources want to hear. For example, if the source is looking for an RIS web server instead of an Apache, then the honeypot should imitate as an RIS in order to hear what follows. And another example would be the source try to authenticate itself through an Windows RPC call, for example, then we should let that authentication go through, and so that we can see what follows. There's a problem that there are too many applications, and the method we take is to go after the dominant ones. And by dominance, we mean that the number of source IPs from which we see this kind of activity. And we hope that this is a metric that captures more or less the global scale of the activity. And this slide shows the structure of our honeypot. I apologize, this light yellow doesn't show up, but what it says is interface. It doesn't really matter. At the very top, we have our honeyd or active sync, which processes our TCP IP level stuff. Basically, they translate IP packets to byte streams for application level responders, and translate byte streams back to IP addresses and send them back to the sources. And at the bottom, we have a tree of these responders. And the high order bit here is that Windows hosts are the main targets. An important part of the responders are Windows CIFS or SMB, the Windows Network File System, and also the Windows RPC part. And likewise for HTTP, RIS is by far the most popular web server in background radiation. And the third class are applications running on Windows hosts. Dameware is remote administration software for Windows hosts. And Beagle and MyDoom are actually viruses, but we can also consider them as a special class of applications. Yeah. Those viruses usually open a backdoor for the binary executable upload, so that they can do software updates over time, and worms are attacking those. Yes.
What kind of coverage did you get of the traffic that just happened over this month?
That's a good question. It actually varies over time. I would say the ballpark range will be 80 to 90% of their source IPs. For the rest, well, this actually is not a complete picture. There are a few more responders there, but we get this kind of range. But it will decrease over time, but it more or less still works for a larger proportion of source IPs. Yeah, but once we start responding, then the majority of packets is no longer. Yeah. And also, each responder usually needs to have multiple rounds of interaction before it gets to see what the intention is. And this is an example shows how deep the interaction can go. In the first connection, the source tries to authenticate itself through the SAMR interface. And once the authentication goes through, it calls another IPC interface to get the time of day. And you may wonder what it is up to. But later, in a third connection, it writes an executable file to the administrator directory. And not shown here, it schedules the execution of that executable file based on the time of day obtained earlier. And I should also say that there are limitations to our responders. They do not try to execute the exploit code received. They also are not allowed to initiate any outgoing connections by the security policy of the institution that are hosting the telescope. Also, those responders are manually built, so an important future direction will be investigate how to build that in an automated way that will make the responder evolve with the traffic. So now we have those responders, and that creates a lot of conversations. The question we have is how can we reduce the traffic volume and still get to see the same kind of picture we see by creating that many connections. And the main technique we deploy is filtering, that we try to suppress repetitive traffic. And our technique is largely based on the earlier observation that the destination addresses are treated the same by the source addresses, more or less. So we hypothesize that if we allocate one destination per source, we'll still get to see the same picture. And by the way, there's also work on building stateless responders for use of, on top of this filtering, for use of much larger telescopes with millions of addresses with certain trade-off. And this is mostly the work of my collaborator, Vinod. And however, filtering is enough for our telescope at LBL. And as we can see here, by allocating one destination address per source, we get the reduction of 95 to 98% in terms of packet volume.
So do you want to give destination what with respect to the first packet the source is sent?
Yeah.
There's nothing about what the sources might want to do after that.
Yeah. Therefore, it's merely a hypothesis. And as you may note, we have two telescopes, so that we can, so actually we get two destinations per source. And we can compare their behavior to see what, and our observation is that they are mostly the same, except in some individual cases where the source will randomly pick one kind of conversation to go on with the destination. And so we will see two different conversations at different telescopes. But in aggregation, we still see both kind of conversation from the different sources, if there are a lot of sources. Yeah, that certainly puts an limitation on what kind of picture we see if the sources have certain behavior. Yet this is so effective that we cannot really do this without filtering.
You're saying that each destination, each source, you're only tracking for one destination.
Yeah, and for I keep a table at the internet gateway, basically to say whether I will let this. So what really happens is that there's a tunnel from the internet gateway to our honeypot. So we decide whether to pass the packet to the tunnel or not. And the way we decide is that for the first destination contacted by each source, we will register that destination with that source. And for all the follow-up packets between these pair of addresses, we will let it go through.
But you won't let somebody else.
Yeah, we will silently drop the packets.
So won't that preference from number one
Interestingly, not, because most sources are actually doing random probing instead of sequential. The sequential scans are from a small number. Yeah. Yeah. By the way, the table expires. The table entries expires every a few hours, so the source gets to talk to another host. Yeah. Yeah.
And the reason you're only seeing that much reduction in volume, because on the face of it, the reduction in volume you get when you want to put nonproductive addresses, right? But it's because you get more packets back.
Yeah. Once we start interacting, then we get more packets.
Okay. And so basically the difference between 21%, which is about what you expect,
Yeah.
you never respond, and this tells you the inflation of the number of packets you're getting.
Yeah.
So,
Yeah.
So if you respond, then you get 100. On order of 100 packets.
Yeah. That sounds like the right number. Yeah, it usually involves tens of packets, or maybe 100 for each.
You're right, it's more like this.
So now we have this, we have already tamed the traffic volume. The next question is, how do we analyze the traffic by adding a passive observer looking at the traffic that we have captured to understand what's going on. And in particular, we want to go beyond TCP/IP. We want to understand, for example, which HTTP URLs are retrieved, which RPC procedures are called. And such kind of analysis must be automated in order to handle hundreds of thousands of connections that we see every day as a telescope. And the way we do that is to use a programming environment that we built called Bro. Bro is originally intended to be a intrusion detection system, a real-time network intrusion detection system. However, it is actually built as a generic traffic analyzer as follows. It contains two parts. There's an event engine, and there are analysis scripts. What the event engine does is it takes packets as input, performs TCP/IP reassembly to get the byte streams, and then parses those byte streams according to application level protocols to generate these events. And events can be considered as the semantic level representation of the traffic. As we see here, they can represent begin or end of a connection, or they can represent an HTTP request with those parameters representing the data fields in that traffic, or they can be an HTTP header. And then the policy scripts can operate on these semantically meaningful events rather than on raw byte streams. And that makes the analysis much easier. It's much easier to analyze the traffic and get what it means at the application level. And then the analysis scripts is basically a collection of event handlers. And within each event handler, we have a pretty generic scripting language, which is strongly typed and has some features that are specifically designed for network traffic processing, such as state expiring and asynchronous communication. But as we see, it is a pretty generic Turing-complete language that this if clause process the HTTP method and do additional processing. And we can also keep states across different events. In this case, we remember which RPC interface is bound to which connection, and that information can be used for later processing.
So you invented a new language?
Well, I didn't. This is collaborative work, but yeah, this is a new language designed for network traffic processing. The reason we did that is that we just haven't found any better alternative. And there are crucial features that we need for this language that we want in the language.
So, when in terms of trying to solve your problem with Perl or Python, what would you say was the main? Is it that you wanted to add a feature to Perl or Python, or is it that you wanted not to have features in Perl or Python and different features, or those didn't fit for some other reason?
There are both cases. This has something similar of what we see in GAPA, that it does not allow, for example, the for statement. So it basically forces the programmer to process the data in a way that it's going to finish in a finite amount of time. And so that's the reduction of features from Perl Parsers. And there are also additional features, such as a hash table with, you can set when to expire certain table entry. And when the expiration happens, an event gets generated, and you can process the expiration event if you want to. And there are also others. For example, you can issue a DNS request, and it will come back later and likewise invoke another code execution. And yeah, but on the other hand, what makes it a powerful tool is that we are able to process at application level. That really simplifies what we want to do with any kind of traffic analysis. And actually, my thesis work has been largely around building this tool and are using it for various traffic characterization and also for anonymization too, as we will see later. And I have been a co-developer of this tool in the past 4 years, I think. And so one challenge we face is that we have to build all these application-level parsers to handle various protocols. There are many message types. For example, in Windows CIFS, we have more than 100 kind of message types. And there are many data fields. And also the semantics are much richer than what we find at TCP/IP level. There are interrelations between these data fields. And so the question is, how do we mass produce such parsers? We do not want to manually construct them. And the work I did is to develop a declarative language to describe these parsers. And then they will be translated into C++ code that will get integrated into BingPack. And this is beyond the scope of this talk, but I will come back to that later in this talk briefly. So now let's suppose we have all these 3 elements ready, and we are ready to tackle the original question as what's the intent of radiation sources? The short answer is that they are trying to take over the victim machines. They are interested in using various ways to exploit the machine to control them. But the approaches vary a lot, and that's what we are interested in looking at. We see a rich collection of applications in the background radiation traffic. And this list is approximately sorted by the popularity of applications, but the popularity do change over time. For example, BitTorrent appeared recently. Yet we find that Windows RPC and HTTP appear to be the 2 most popular protocols we see in the traffic. And that's the 2 protocols. We will have a closer look into them in the following slides. VMware is remote administration software. The software itself, I believe, is not very popular, but for some reason, the vulnerability is very popular. Yeah, maybe that has a reason. It's due to that exploit is integrated into a very popular malware, which has many exploits. So that's why we are seeing this on our radar. So what's inside Windows RPC traffic? By the way, it is the most active protocol in background radiation. It is found in a number of ports, either standard ports or non-standard ports, like 1025, and also over CIFS named pipes. So when we see traffic on those ports, we are actually much more likely to see Windows RPC traffic rather than network file system traffic. We also observed a wide range of services and functions within this RPC traffic. There are 19 interfaces and 82 functions during a few months. And to give you a sense of what the range is, last year we also did a study of LBL's enterprise internal traffic, that is, represents the normal use of our network. And we see 14 interfaces and 68 functions, however, for a shorter period of time. Yet that gives you a sense of what the range of functions. However, I should also mention that this only represents a small portion of all available Windows RPC functions, which is a giant collection of functions. Yeah, yeah. Yeah, yeah. I would just say people do not patch them. Still out there. Yeah. Yeah, we still see code red, for example. And yet, the most sources are targeting these are the most popular interfaces. It's very concentrated. And let's look at one of them. This is a very juicy vulnerability in the sense that it affects Windows systems from 95 to Server 2003. And the best known malware that exploits that vulnerability is the blast worm. The infection actually takes two steps. First, it tries to buffer overrun the RPC function with this fixed payload, which creates a remote shell on TCP port 4444, meaning that for any payload it accepts from that TCP port, it will execute those payload as Windows shell command shell. Then the worm will send commands to that port. First, to download the binary executable from the source with TFTP, then to start executing the file. And such kind of two-stage infection is widely observed in background radiation traffic, and I believe it has some significant impact on the landscape of background radiation we see, because as you can imagine, this makes our creation of malware much easier than before. For example, the single-stage exploit of code red, which has to embed all the code into the buffer overrun code. Since remote shell code can be reused, and there are many versions of their public on the internet. So if one knows a vulnerability, one can plug in a remote shell, then it's much easier to create a binary executable that propagates the worm than to embed that into buffer overrun. And for this reason, Blaster actually accounts for less than 1% of the source hosts that we see on this vulnerable interface. Instead, there are many, many variants of this malware, and almost all exploits appear to use this remote shell mode. However, sometimes there are no follow-up connections. And we looked up literature on the internet, and there are some saying that the victims will phone home instead by embedding the source address into the buffer overrun code. And we actually tried to verify that and succeeded. Then we were warned that we are not allowed to initiate any outgoing connection or risk losing the telescope altogether. Yeah, we can certainly try to read that, but we didn't. It's beyond the scope. Now let's turn to HTTP. The dominant activity is a search request with a very long URL. It's more than 30 kilobytes. The URL is not fixed. The vulnerability it seems to target is the NTDLL vulnerability. It's also an old vulnerability. The targets are RS servers with a certain web dev component enabled. And therefore, interestingly, the sources first try to probe whether the servers have that vulnerable component or not before it sends over that large exploit code. And so in that case, we need to imitate as if the component is there to the previous two commands. And if we look at this attack URL, it looks quite weird in the sense that we are not really seeing a binary code here. Instead, there are a bunch of lowercase letters that one would not expect to see in a buffer overrun code. What's going on here? And what happens is that the initial part, which is encoded in Unicode, represents a short decoder which will decode the following payload. Each letter represents 4 bits of the execution code. And it will write the execution code to the memory chunk and then start executing that. So that hopefully shows how sophisticated these things become. And one reason it does that is because the URL will go through a Unicode decoding, which will insert a byte 0 after every byte. And however, I do not know why they do not do all of this with this Unicode encoding. And however, this is not the only thing we find in HTTP. We also find the code red 2, which was set to expire in 2002, but somebody changed the expiration year and re-released it. And also, the namebar worm is also visible on our radar. And also, we see this ticketbar.net, which are sent to the HTTP proxy port. And it requests a URL like this. And as we look at the website, it's an online advertisement software website, which gives you a small amount of money when you click on it. And what it does is it tries to recruit HTTP proxies as the downstream users. You also get revenue by developing downstream users. So that you can...
So it's trying to trick random machines. They basically make zombies go and click on that thing and hope that whoever owns it will give them a lot of money.
Yeah, yeah. And you can see that there's an ID here, which probably points you to... By the way, that website went out of business later that year. I do not... So far we have seen that we are really facing a lot of malicious software in the background radiation. So naturally the question is, can we build a monitor that will help us answer questions such as, what's the dominant activity? And perhaps more importantly, what's new in the background radiation? What's new in the malware world? I think there are 2 key challenges here. This is a part of ongoing work. So I'm offering what we have here. And one challenge is to evolve with the traffic because we are monitoring it all the time for a long period. And another challenge is, how do we get an abstract and succinct description of the background radiation traffic so that we can reason about it, because there are really a large variety of behaviors that we see in the traffic. So what it takes is to classify the events at a certain granularity that it will produce a concise description of what the landscape looks like, and which also would allow us to detect new activities. So the question is, what's the right granularity to look at things? So the design space is plotted here. The x-axis is how close we look at each event, how much we zoom into the traffic. We can look at coarse grain at port or application, or we can look at which application level function are being invoked, or we can look at what's the length of the exploit, what the exploit code is trying to do, as we look closer and closer. At another dimension is how much we aggregate those behaviors. We can look at by individual requests, or we can look at the request sequence of a connection, or by look at all the interaction happens between a pair of hosts, or we can look at a profile of a certain source. And for example, if we are interested to know which malware is most active, then we probably should look at exploit characteristics and create source profiles based on that. That will allow us to identify what are the new malwares out there. And this is actually the original approach we took when we tried to create profiles of background radiation. However, what we found is that because of this, probably because of this 2-stage infection model, there are too many variants out there, as we will see shortly. And whenever a new exploit comes out, there are a bunch of variants following up. And also, as time progresses, a malware tend to use many exploits at the same time, yet we do not get to see the complete vector in our observation. So the problem becomes a high-dimensional clustering problem because we are trying to approximately matching which two sources are running the same malware. So that problem turns out to be hard. Another question we may ask is, what's the most popular application being targeted in the background radiation? And by doing that, we only need to look at the port number to figure out the application, and by looking at individual applications. And I believe one juicy spot in this is to look at which vulnerabilities are being targeted. This basically follows the same idea as the SHIELD paper, that we should take a vulnerability-oriented view of things. And depending on the vulnerability, we need to either aggregate, either by looking at individual requests or by looking at connection or session behavior. But we only need to look at application-level behavior. We do not need to care about which detailed exploit it is. And in our experience, we find that we can usually tell the vulnerability by looking at individual requests with certain context information. For example, we know that which RPC interface is bound to that connection. And once we know that, we can usually tell that this is different from another. And perhaps one advantage of this is that we do not have to have some existing knowledge about all the vulnerabilities out there. Instead, that can detect whenever a new vulnerability appears that we do not previously know. So this is the approach that we took, and let's look at what we have seen. So this is the daily Geiger counter at LBL, which is number of source IPs we see every day in the past 2 years, except for the small gaps here that we do not have data. And you can clearly see that the peak is around the time that the Sasa worm outbreak. And we want to know what happened during that event. And this graph shows the number of source IPs from which we see the Sasa exploit. And note that there are several peaks here, which is pretty curious. And indeed, if we plot the backdoor behavior of the Sasa worm, this is the first Sasa worm. As we can see, around May the 1st, it closely follows the Sasa exploit. However, later on, there are gaps here. And what happens is that there are variants closely following the initial worm. For example, this is the second Sasa worm, which explains the gap between this one and that one. And then there are further worms out there. And we can see that the exploit remains a threat even after the initial worm subsided. And actually, we continue to see the Sasa exploit on the background radiation today. It remains to be the main activity. And here's one thing curious. Before the backdoor behavior, we already see the exploit, even before the worm was released on April 30th, I believe. And that points to something interesting. So that might be a test run of the Sasa worm before it is officially released. Maybe the attempt was not successful, or maybe it's from a different person because the exploit was already published on the internet. Yeah. But that is promising because if we take a vulnerability-oriented view, we might be able to detect the upcoming malware before it is successfully built and released on the internet. And by the way, malwares are carnivores. They eat each other. And in this case, wheelchair used to be the dominant malware on our radar. And as we see, after the first release of SASA worm, it took a hit and never actually came back. And after perhaps another variant of SASA worm, it's almost completely killed. And it remained the case. Well, in some cases, worms do come back, though, but not in this case. So as a summary, we have developed a set of, yes? I don't know, because we do not look at the exploit code. But based on past history, for example, code red 2 kills code red 1. And it does that by patching the software, closing the vulnerability, and also killing the existing malware if it exists on the machine.
The first thing I do in my body is go up with
Yeah.
Body zombie.
Yeah.
And then eventually, like if that comes out with malicious software that implement backs, which is presumably why you see
Yeah.
drop off.
Yeah. Yeah. One guess will be it's due to our Service Pack 2 being released. Then people start patching their systems. We are seeing this.
Service might be turned on the automatic updates.
Yeah, and also firewalls are turning off those ports by default.
Firewalls, although that wouldn't stop the output.
No, it won't. Yeah. Yeah, but maybe there's a gradual update of the population that.
Microsoft has been pushing tools on once-a-month that looks towards malware and so
I see.
we've got to advocate one of those updates that was most
I see.
and also yes, it'll malware just getting away from away.
Yeah. Yeah.
For 4 years, they've not what, now 6 years long have the machine be around, and machines that have down there, the using it is not vulnerable, so
Yeah.
it's just easier.
Yeah. Yes. By the way, what's happened recently is that we are seeing more and more of botnet activity rather than big worms. If I have time, I will go through that. What we have developed here is a set of measurement methodologies. We try to respond at application level. We build filters. We analyze traffic automatically to extract the meaning. And I also believe that classification by vulnerability appears to be the promising direction to go if we want to build a malware monitor. And the background radiation appear to have universal coverage in our experience, and it's largely 24/7. It's not really largely, it's truly 24/7. The traffic is highly automated and often malicious. We also see this two-phase infection model, and which probably led to our easy creation of variants. The malware is also constantly evolving. What I didn't show in my slides is that the SASA exploit quickly gets integrated with the old system activator, the blaster exploit, and malwares are quickly adopting new exploits over time, and also malware kills malware. What I also didn't show is that it's not only worms. We also see controlled botnets, which does coordinated scans on the order of tens of thousands of hosts at a time. So this study is actually a part of a bigger effort that we call network traffic programming. That is, in general, we want to analyze the meaning of internet traffic in a rich, stateful, and application protocol-aware way. We want to easily build analyzers that will, based on the meaning of the traffic, and there's something. And what we also want to do is to transform the traffic, not only to understand the meaning, but also to change that, also at a semantic level. And this has several impacts. One is that it represents a new direction in our understanding of the internet. A lot of work has been concentrated on understanding how bits move around on the internet, such as routing or congestion control. And on another dimension, we may ask, what's the meaning of these bits? And by understanding this meaning, in some cases, that helps us to understand why bits move around in the first place. And also, it helps us to build new network intrusion detection techniques, or perhaps more generally, traffic certain security policy on the traffic. You want to allow certain type of traffic to go through while disallow certain others and transform certain. And one example will be application level firewall, as outlined. I'm sorry.
I'm trying to understand this slide, talking about putting smarts in the middle of the network to transform traffic into complicated semantic level things, or applications other than things like honeypots and also where you kind of the endpoints.
Yeah, so
Isn't that going to interact extraordinarily badly with the traffic, the type of lanes that we involve with all the traffic on the network?
Yeah, that's a good point.
I asked this question to Andy.
So one way to answer this will be the main scenario for network intrusion prevention will be at the gateway of enterprises networks, for example. And in that case, currently we do not see a large portion of encrypted traffic. Yeah.
Very strong, and the cost of the second level.
So perhaps, I don't know, perhaps there might be some administrative process that will allow the network intrusion prevention system to understand, to look into this encrypted traffic. Yeah.
Okay, I mean, coming off from that, whether traffic's encrypted or not, what the heck is this stuff going to do? I mean, what function do you want to put in the middle of the network walking around with traffic?
So one particular application will be a traffic normalizer, which is very useful for intrusion detection. For example,
never mind security stuff, right? I mean, is there anything other than saying trying to stomp out this malicious traffic?
I don't know. We will see if we have this technology ready.
Okay, but
Yeah.
then we're not talking about it in the middle of the cloud. We're just again talking specific choke points, firewalls, that sort of stuff.
Yeah, that's actually. I'm also not talking about the middle network. I believe there is a very long way between right now and we can deploy such a system in the middle of the network, which is going to handle a very high volume of traffic.
Okay.
But I'm really talking about around the edge of the network.
So it sounds like socks on steroids. Why is this hard? I mean, what are the research problems here?
Sounds like, I'm sorry.
Oh, socks? I mean, so people have been doing application layer proxies and all sorts of packet rewriting at the end of the network forever. I mean, I don't have a sense of what's the research problem here.
Well, I guess the research, Helen, do you want to?
Go ahead.
I guess the research problems will follow once we have the technology ready. So that's
Okay,
so.
that's the disconnect I have. People do all this stuff right now. I mean, the infrastructure is all there.
Can you give me some examples of?
Okay, so many enterprises today have some kind of proxy to mediate.
Yeah.
activity
Yeah.
outside of
Yeah.
often big forms of the stateful firewalls,
Mhm.
create dynamic state, TCP forwarding, simple heuristic connections go out, and with connections can't originate coming in. Then there are application layer proxies like socks, which actually split connection So sort of like transporting some of the sockets from your internal client to the outside of the firewall. They often then do mediation as well, URLs, some of them processing to make sure that their signatures and all that. So that infrastructure is all there.
So that's the gateway services for monitoring the traffic, malicious traffic behavior protection.
Is that the only difference? I mean, SOX, so SOX does that kind of signature stuff today, right? I mean,
SOX is because the client is set up to go through the SOX, so the
Right.
clients are corporate. But here we have all kinds of traffic coming from outside.
well, yeah, but okay. So the claim is that I want to allow all that random traffic into my network. So this is the question of how. The challenge is how porous can I make my firewall so that even unexpected, uninvited traffic can still get in, and I just throw away the benefits of it.
So as I understand, what you are saying that there are host-based approach to tackle the same problem, which operates at socket level. And what we are doing here is trying to replicate that effort at network level. Is that, did I get it right?
Okay. We'll talk more.
Okay. But the short answer is that there are advantages of doing that at the network level because we are seeing a bigger picture here that we can get collective information about what's going on at network-wide range. For example, for certain scans or other activities, it's necessary to look at multiple source-destination pairs in order to figure out what's really going on.
So the claim is that by looking across traffic in general,
Yeah.
it would be smarter than particular client.
Yeah, and also this has a deployment advantage that we do not have to modify every source host. Do not have to install something on individual source hosts, but it's much easier to put something on the network from the administrative point of view. We'll see. It's still an open question of whether we should do this at host-based approach or with a network-based approach. And the current status, I believe, is that neither approach seems to have solved the problem yet. So let's see what approach will be the better approach in future. So my efforts in this area has been built around the broad programming environment. We have just seen this study of internet background radiation that we try to extract the meaning of the traffic. I also have done worked on enterprise network traffic, packet anonymization, and the language for building protocol analyzers. Let's go through them briefly. In the enterprise network traffic, the question we are interested are, first, what applications are driving enterprise internal traffic as opposed to wide area traffic? The quick answer is that we find a much richer of applications within the internal network. And the second question is, for applications that are common in internal and wide area traffic, how do they different? How the application level behavior differ from each other? And we also look at what about those previous unstudied protocols because they do not exist in wide area traffic, what their application level behavior looks like. This is our enterprise study. And the system we built about understanding the meaning of the traffic can be also used to anonymize traffic at semantic level and to solve this problem of lack of packet traces. What happens today is that packet traces are very useful, but they are rare because they contain all kinds of sensitive information. So, and in particular, in order to understand the packet trace at the application level, we need packet traces with application level data preserved, with sensitive information removed, but the rest preserved. And our contribution in this work is about how to identify and transform sensitive data fields and how to preserve the original structure. And and in general, how to build a programming environment to make that process easier. And the current ongoing project is BingPack, which is a domain-specific language for building protocol analyzers. I believe it has a lot of overlapping with GAPA. But our target is slightly different because we are targeted to be compiled into C++ code so that we can process at high speed at network level. And another direction we are looking at is whether we can take that information and translate that into a parallel program or even FPGA representation of network processing, and which will allow us to build our network analyzers in hardware. And one feature I'm going to show you is what we call data dependency driving processing. So this is the header of an SMB message. As you can see here, that there are interdependencies between fields. This error status depends on the error status type, which is computed from this flag true, which is a later field. And the reason we can parse our flag true before this is because this error status, no matter what the type is, has a constant size. So the compiler decides that it's possible to do that. Then it will first process flags true before processing that. And the same kind of dependency analysis can be used to skip fields that are not going to be used by later analysis, so that basically we can trim the parsing to the specific analysis with this kind of language. And that allows us to build high-speed network parsers. I also have worked on other research areas, as shown here. I was an intern at MSR 5 years ago, working on software protection. And that's the end of my talk. And thanks for coming.